let's explore how to tell whether or not two fractions are equivalent. So two fractions a over b and c over d are said to be equivalent fractions if AD is equal to BC. Now fundamentally what equivalent fractions are they're different fractions, but they represent the same concept or the same quantity or the same part-whole relationship. So because they use different numbers, that tends to goof us up, right? We're kind of very used to if I write a 4 versus if I write a 6, I'm talking about a very different quantity, right? But in fraction world, I could write two different fractions, and I'm actually talking about kind of the same number, if you will, or the same quantity. So we want to know if, when we're looking at two fractions, if the two fractions are equivalent to each other. So kind of talk about this idea that I could have two different fractions, that the numbers look different, but I represent the same quantity. I have this circle here that's divided into 8 equal sized pieces, and 2 of the pieces are shaded. So in the circle, if I wanted to write a fraction for what's going on there, I could write the fraction 2/8. Now one of the key things about fractions is that we have to be able to take our whole and divide it into equally sized pieces, and then the denominator tells me how many of those equal sized pieces it took for me to make my one whole. So on this, and so I just have a replica of this same circle, and all I'm going to do is I'm going to divide it into smaller pieces. So I'm going to basically take every one of these triangle sectors and I'm going to cut it in half. All right, so just bear with me because I'm freehanding this here. It's obviously a little bit easier if you can have a program do these lines nice and neat. Okay, but I'm just going to cut this into smaller pieces. So at this point in time then, how many pieces would it take for me to make my one whole? So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it would take me 16 pieces to make my one whole. And then how many of those pieces would be shaded? 1, 2, 3, 4. So I haven't changed how much is shaded. I've changed the size of the piece, but what's going on right here and what's going on right here has the same part-whole relationship, right? I haven't changed how big the hole is, right? Still is one circle to fill one hole. And over here, then I've just changed the size of each piece, but now also I have more pieces. So it has the same relationship of shaded to the entire thing in both cases, but the numbers are obviously very different. Now if I want to test whether or not the fractions 2/8 and 4/16, if I want to see if they're equivalent fractions, or in other words if they're equal to each other, what we can do is multiply the numerator here times the denominator here. So 2 times 16 is 32, and then I can multiply the denominator here and the numerator here. So 8 times 4 is 32. So since I got the same number on both of those multiplications, these two fractions are in fact equal to each other. In other words, that they're equivalent fractions. Just as a fun little fact, if you do your multiplication by always going from bottom to top, you can also compare or order two fractions. Meaning if I wanted to compare, for instance, like 5, 6, and I don't know, we'll say 9/11ths, and I want to know how these compare to each other. Is one bigger, one smaller, or are they the same? Are they equivalent? So again, if I kind of multiply from bottom to top, 6 times 9 is 54, and I would write it up here, up on the top. If I multiply from bottom to top, 11 times 5 is 55. And since 55 is bigger than 54, obviously these two fractions are not equal to each other, but the relationship that would exist there is that 5/6 is greater than 9/11ths. And I can determine that just by looking at the size of these two numbers up here. Now to order fractions, some people convert them into decimals, but that requires you to have a calculator. This just allows me to kind of use some multiplication facts in order to determine if these fractions were equivalent to each other, or if one of them was bigger, who the bigger fraction was. All right, so when working with equivalent fractions, two really important things. You can multiply both the top and the bottom of a fraction by the same number to create an equivalent fraction. And you can divide both the top and the bottom by the same number to create an equivalent fraction. So as an example, let's start with a fraction. How about 3/4? If I multiply both the top and the bottom by the same number, so maybe I multiply both the top and the bottom by 2, and I get 6/8, what we have just found is that the fraction 3/4 is equivalent to 6/8. Now you can multiply the top and the bottom by whatever you want. So just as another example, I could have taken the fraction 3/4 and maybe multiplied both the top and the bottom by, I don't know, 10. So if I multiply both the top and the bottom by 10, I would get 30/40. So then what we have just found also is that 3/4 is equal to 30/40. So you can see you can create an infinite number of equivalent fractions to a starting fraction by just changing what you multiply and divide the top by. Now you can also divide both the top and the bottom by the same number to create an equivalent fraction, but when you do the division you have to pick something that would divide both numbers evenly. So as an example, if I have like the 2/8, I can divide both the top number and the bottom number by 2 because they're both even, and I could get 1/4. So then what we just found was that 2/8 is equal to 1/4. I would not take the 2/8 and, for instance, divide both numbers by 4. 8 divided by 4 is 2, so that one divides nicely, but 2 divided by 4, that does not divide nicely, right? So when we do the division, we have to make sure that we pick something that divides both upstairs and downstairs. So just as maybe another example, 30/40, we can divide both of those by, obviously, by 10 to kind of get back to what I did up here. So 30 divided by 10 is 3, 40 divided by 10 is 4, but you could also divide it by, for example, I don't know, 5. 5 goes into both of those numbers, so 30 divided by 5 is 6, and 40 divided by 5 is 8. So what we just found is 30/40 is equal to 6/8, but it's also equal to 3/4. So every one fraction can have an infinite number of equivalent fractions, but one of the things when we're working with equivalent fractions is we try to find a fraction's simplest form. So the definition of simplest form is a fraction that is considered to be in that form, simplest form, if the only common factor or the only common thing that divides the numerator and denominator is 1, because remember 1 divides everybody. So as an example, 2/9 is already in simplest form. The only thing that divides 2 that also divides 9 is 1. In order to see whether or not something divides both of those numbers, it's sometimes helpful to think about it prime factorization. So 2 is already prime, so I can't break that down any further, but 9's prime factorization is 3 times 3. So what we can see when we look at the prime factorization is that there's nothing common both upstairs and downstairs. So there was nothing I was going to be able to divide out. So then the fraction that you're looking at must already be in simplest form. So as a second example, 10/15 is not in simplest form. If I look at its prime factorization, the prime factorization of 10 is 2 times 5, and the prime factorization of 15 is 3 times 5. And I'm seeing something both upstairs and downstairs in that prime factorization. So that thing is what I could divide out. Sometimes when we have this prime factorization form, we say we can just cancel it. So we maybe put like a little slash through it to just show that we're going to divide it out or remove it. So 10/15 in simplest form would be 2/3. As a last example on simplest form, let's take a look at the fraction 24/30. Now if you're looking at those two numbers, perhaps you notice that both of them are even, so maybe we divide out a 2. So 24 divided by 2 is 12, 30 divided by 2 is 15. Now at this point in time you would have to reassess the fraction 12/15 and ask yourself, does anything continue to divide both of those numbers other than 1? And in this case, 3 goes into both of those numbers, so we can divide out a 3 from both of them. 12 divided by 3 is 4. 15 divided by 3 is 5. So now we would ask ourselves, does anything go into 4 that also goes into 5 other than 1? And the answer to that is no. So at this point in time, we're done, and then we found that the simplest form of 24/30ths is 4/5. Now, as opposed to doing this kind of piece by piece, what we could do is we start thinking about the largest thing that goes into 24 and 30, which is called the greatest common factor, or the GCF. So the greatest common factor of 24 and 30 is 6. That's the largest thing that divides 24. That also divides 30. If you can think about finding the GCF, you can get to the simplest form kind of in one division, but it's not wrong to kind of do it piece by piece. Just, the GCF saves us a little bit of time. If we take a look at the prime factorization of both of these numbers, the prime factorization of 24 is 2 times 2 times 2 times 3. The prime factorization of 30 is 2 times 3 times 5. And if I look at what's both upstairs and downstairs, I see a set of 2's that are in common, and I see a set of 3's that are in common. So if I cancel those out, there's also where I can see that GCF was 6, right? Because 2 times 3 is 6. So just kind of another way of seeing it or thinking about it. So one of the things to know is that when we present a fraction to somebody, we normally will always present it to them in simplest form, because the idea is that there's that simplest representation for that part-whole relationship. So it's really easy for us to see if you and I are talking about the same fraction, or are we talking about different fractions, right? So we don't want to be like, I'm looking at 10/15, and you're looking at 2/3. Are we doing the same, are we looking at the same fraction, or are we looking at two different fractions? If we both just present it in simplest form, it's easier for us to tell. Now, one of the things for fractions that I think is very important is to be able to work with flexibly with halves, fourths, eighths, and sixteenths, but because it connects to how we do measurements in inches on our rulers. All right, so I kind of have these as a diagram over here. So my 1 whole, or my 1 unit, would be the distance from here to here, right? So this would be my 1. So for halves, 1/2 is equivalent to 2/4, which is equivalent to 4/8, which is equivalent to 8/16. So being given any one of those fractions and being able to very quickly simplify it down to 1/2, or being able to scale it up if, for instance, we have to do operations involving adding or subtracting, is a very kind of important math fact family to have memorized. Similarly, the fractions 1/4, 2/8, and 4/16 are equivalent to each other, with the 1/4 being the simplest form. But sometimes when we're given 1/4, we might have to work with the 2/8 or 4/16 if I'm thinking about maybe adding or subtracting fractions. Same thing with the 3/4, that is equivalent to 6/8 and 12/16, so being able to go back and forth kind of between those facts. And again, to get to the larger ones, so for instance, if I want to go from 3/4 to 6/8, all I did was multiply the top and the bottom by 2. Or if, for instance, I was given the 12/16, to get back down to simplest form, I could divide both of those by 4. So remember that you're allowed to multiply both the top and the bottom by a number, or divide both the top and the bottom by a number. So this is kind of an important set of numbers to be able to work with and be able to go back and forth very quickly, because you'll see a lot of applications with these. If you go to measure something, you got to be able to work with halves, fourths, eighths, and sixteenths.